Okay, so today is week 6 and today's theme is energy conservation and momentum conservation, and most of the problems we'll be solving will be using the concepts of this. um, let's start. It's 3:05. So the first question is, a car can go from position A to position B along three possible planar roads: AB, that is this, straight go from A to B, A to C to B, or A to D to E to B, as shown in figure. Assume gravity acts perpendicular to the plane of the path. So gravity acts perpendicular to the plane of the path. If the drag coefficient due to air, okay, so there is drag coefficient, so air resistance is there, and the speed of the car is the same along all the three of the paths. So whatever direction you go, the drag coefficient is there and you go enter with the same velocity. Will the fuel consumption of the car be the same along all three paths? So the question is, will the fuel consumption of the car be the same along all three paths? Now the fuel consumption will depend on work done. Okay, so work done due to the car speed against the air resistance. Remember, the gravity is acting perpendicular to all of the directions, because it is acting perpendicular downwards on the plane. So the first one, yes, the fuel consumption will be the same. Yes, because all three roads starts from A to point B. So now the point is, the work done depends on the length of the path it's taken. So it can't be yes, any yes, it would not be equal. What is the reason? No, because cross section of the card will be different along different roads. Cross section of the card is not correct. Work done by the drag coefficient friction will be different along the different roads. So work done by the drag force will be different because the length of the roads are different. So work done is force times displacement, right? This is the displacement. So this displacement is different along AB, ACB and ADEB, even though the drag force is same. Okay, so the last option is correct. Okay, next question. A slider whose mass is 1.2 kg. So mass is given, a slider is 1.2 kg, can move along a path. So this is the slider A. So it has mass, let's write it down, 1.2 kg. It can move along a path. This is the path. To compress the spring, so if it can move like this and come here and compress the spring as shown in figure. The slider is released from rest position at A and slides without friction, so there is no friction along the vertical plane guide. The speed Vv of the slider as it passes position B. So you have to find the speed Vb as it passes. So this position B. Okay. So let's take this as the base, z equals 0. So this is the base, so there is zero potential energy. Now higher you go in this direction, positive z direction, let's say, you gain gravitational potential energy. So at A, it was at rest. So kinetic energy E, let's write it like EK at A is 0, and energy, potential energy at A is, should be mgh, right? And what is this h? H is 3 meter plus 1.5 meter, right? So h is 3 meter plus 1.5 meter, which is 4.5 meter. So the total energy is at A is, so E total at A is mgh. Okay, now let's say it has fallen like this under the influence of gravity and reached this point B. Now at this point B, what is your at B kinetic energy? Kinetic energy will be half mv square. So let's write velocity at point B is as vb, so it will be half mv square. Now what is the potential energy at point B? So potential energy was measured, we are defining this to be our ground, so there is no potential energy here. So the total energy E total at point B is half mvb square. Now this was done without any influence of external force. It is a system except gravity, and there is no friction, and slides without friction, there is no air resistance, so the energy should be conserved. So E total at A should be equal to E total at B, which implies half mvb square equals mgh. So this guy and this guy, these two are equal. Okay, now you are asked what is vb. So vb equals, so mass gets cancelled out, root 2gh. So root 2 into 9.8 times 4.5. Here we calculate h is 4.5, and the unit will be meter per second. So if you calculate it, you will get around 9.4 meter per second. Is there an option? Is the option A is correct option. So you can calculate like square root of 2 times 9.8 times 4.5, 9.39, which is 9.4 megawatt. So this is our answer. Fine. Simple problem, just do an energy conservation and you are good to go. Okay, so next question. So it is a related question. In figure of question 2, what is the maximum deflection delta of the spring? So what is the maximum deflection delta of the spring? So let me try to grab this. No, let us take a screenshot. Copy, done, delete, copy and delete, and paste. Nice. Okay, so this, remember this was falling, and this is falling, goes here at this point E, and this starts compressing. Now, due to the conservation of energy and momentum, conservation of energy, so whatever energy it starts from here, this should be the total energy should be same till this point, and if it compresses, it will compress with the same energy. Okay, so let's assume the maximum deflection is delta. Now, so for this deflection, the energy stored in the spring is half k delta square, right? So energy stored in the spring is half k delta square. Fine. Now this half k delta square energy will be given by this slider. So now whatever the energy was here, it goes it loses potential energy here and gains kinetic energy. Then when from B to E, when it travels up, it starts slowing down, right? So and eventually it loses some kinetic energy and some potential energy. Okay, now at this point, so at this point it will have some potential energy, and this is what it will press you with, right? Now if we can find what is the potential energy at this point, what is the energy at this point, you will be good to go, right? So what is the energy at this point? So whatever the energy is, we don't have to calculate the total velocity at point E. Why? I'll tell you. So from this point we have some energy, it goes like this and it loses some potential energy here. So for this point it is mgh, right? And from this point to this point, this is the total energy. Total energy at A is mgh, right? Now let's say total energy at E equals something. So E is E, at E is E. Let's say E, or let's say it is U. Okay, now you can have like a half mv square plus some elevation, right? So this, let's say I can write half mv square plus some mgh2. Let's say this is h2. Now v square we don't know. The trick is you can actually calculate v square from this equating with mgh and all of them, but you don't have to calculate. You don't have to calculate. Why? So mgh equals half mv square plus mgh2. Okay. Now then so I write it as kinetic energy Ek. So Ek equals mgh minus mgh2. So this kinetic energy will be transformed to half k delta square, right? So the kinetic energy it has at this point will be transformed to will be used to compress the spring. So mgh minus mgh2 equals half k delta square. So delta equals 2 mg h minus h2 by k. This is delta square. So 2 times m is 1.2 kg, 1.2 g 9.8. H minus h2 is basically this length. So this is 3 meter. So this is 3 by k. K is here. See, k is given here, 24 kilonewton per meter. So k is 24 times 10 to the power 3. Okay, so let's calculate this. 2 times 1.2 times 9.8 times 3 by 24, sorry, 24 times 10 to the power 3. So this gives 0.0029 meter. So delta becomes square root of this. So 0.05422 meter, which is equals 54.2 millimeter. So this is our answer. So 54.2 millimeter. Fine. Is it not visible? Yeah, it is visible. Okay. Next question. For figure A shows that the orbit of the moon around the earth around the earth under the sole influence of the earth's gravity. A, B, C denotes three positions of the moon along its orbit. So moon along earth and comet around earth. Assume the orbit to be circular. So moon's orbit to be circular. Verify if it is a reasonable approximation. Figure B shows that elliptical orbit of a comet around the sun. This should be sun. Comet around the sun and the sun under the sole influence of sun's gravity which is always directed from comet to the center of the sun. A, B, C, D, E are 5 different positions of the comet along the orbit. Which of the following statements are true? So the Earth's gravitational force can change the momentum of the moon, but not kinetic energy of the moon. Is it true? So Earth's gravitational force can change the momentum of the moon. So momentum depends on mass and velocity. So if the Earth's gravitational force can change the direction of the moon's velocity, then it can change momentum. So for any given position, the direction of the velocity is tangentially outward to the orbit. So this is correct. The moment it can change, and but cannot kinetic energy. Yes, so kinetic energy cannot be changed because there is no this whole thing, Earth and mass. Earth and moon is a closed system. There is nothing. You are assuming there is no external perturbation here, external force there. So the kinetic energy of the moon will not be changed. So A option is correct. So Earth's gravitational force can change the kinetic energy of the moon, but not the momentum of the moon. Wrong. In figure A, the Earth's gravitational force is doing work. In figure A, the Earth's gravitational force is doing work to move the moon from position A to C. In figure B, work done by the sun to move the comet from position A to C is 0. No. So for the third option, so Earth's gravitational force is doing work. So if it is a circular orbit, then the displacement and the force are perpendicular. So the dot product becomes 0. So Earth's gravitational force is not doing work. So our work done by gravitational from A to C is 0. The sun's gravitational force is doing work from comet to, because this is not perpendicular. So here, so let's say at B, like this and this. So this two dot, so this is the displacement direction, let's say x, and this is the force. So this would not be 0, and here it's always perpendicular. So if it is perpendicular, it is 0. So D option is another correct option. So next question. So particle of mass m moves towards x equals 0 under the influence of the potential V minus A minus A mod x whole to the power n, where A greater than 0 and n greater than 0. Suppose that time t equal to 0, the particle starts at some place on the positive half axis of x axis. Particle has just enough energy to reach x equals 0, that is, it stops upon reaching the origin x equal to 0. For what value of n will it reach x equals 0 at finite time? So let's say, so energy, so let's say this is our point A, okay, and this is point O. So let's say this A is x0, 0. So energy at point A. What is energy at point A? So half mv square, because there it has a velocity v, plus some potential energy that is given, right? So x0 is greater than 0. Okay, now at O, so energy at point O is 0. Why? Because it stops at O, so there is no kinetic energy, and then also at x equals 0, this Vx is 0, so it is 0. So half mv square equals minus Vx. So half mv square equals a x0, right? No, sorry. So a x to the power, so a x to the power n. So vx is a x to the power n. Okay, so we'll write at x0 what is we'll put information about x0 after we integrate, when we are calculating x. So then v becomes 2a by m x to the power n by 2 root minus. So why are we taking the minus sign? We are taking because velocity is in this direction and positive x is in this direction, that's why we are taking minus sign. If we take plus sign, then we have to reverse the coordinates, so we have to make velocity at along this direction and integrate. When we integrate, we will integrate from 0 to x0. So from because of this we are taking minus sign. So minus sign comes because it has a different direction of the as a position. So x is defined as positive from this direction and v is in this direction, so x and v has opposite sign, so it could be plus minus, so we are taking the minus sign only. Now we write v as dx dt n by 2. Let's integrate. So dx by x to the power n by 2 equals minus root 2a by m dt which equals x to the power minus n by 2 dx minus root 2a by m dt. So integrate 0 to 2 at t equal to 0, it was at x0, and at t, at some finite t, we are assuming. So we are assuming for some finite t it reaches x equals 0. So the integration gives x to the power minus n by 2 plus 1 by minus n by 2 plus 1 x0 to 0 and minus root 2a by m t. Okay, page. So 1 by 1 minus n by 2 0 minus x0 to the power minus n by 2 plus 1 minus root 2a by m t. So this minus sign and this minus sign gets cancelled, so we get t equals root m by 2a, so this times 1 by 1 minus n by 2 times x0 to the power 1 minus n by 2. Now for this t to be positive, we have to have 1 minus n by 2 to be greater than 0. This has to be positive. So n by 2 is less than 1 and n less than 2. So this is the condition for the particle to reach the origin in finite time. Okay, so n less than 2 is the answer. This is the answer. Okay. Okay. So we have 3 more questions left. So next question. On the small marble is placed on figure with a velocity 3 meter per second. So it has a velocity 3 meter per second, direction of 15 degree. So can I redraw it? Let's try. Let's zoom and redraw. Really big. So now it says that there is a ball here. So this is an angle, let's say this is phi. So phi is 10 degrees and this is our y direction, and along this we have x direction. Okay, now with y direction it has a velocity v, so with a theta angle. So v is 3 meter per second and theta is 15 degree. Okay, so smooth incline, there is no friction. Calculate the magnitude v for this velocity after 2 seconds. So after 2 seconds we will have to calculate the magnitude v of its velocity. So how would you calculate? So initially v is 3 meter per second. So what is the magnitude? So let's components. So let's create components. So this velocity has a component in this direction, so which is v cos theta, and in this direction v sin theta. Okay, and we also have gravity acting like this, mg. Now for this gravity, this angle will be 90 minus phi because of the inclination. So you can prove it by drawing this. So this and these are parallel, and this will be phi, and this with the inclined, and let's say this is our inclined, and the perpendicular straight downwards will be our, so this angle makes phi, and the other angle along the inclined plane should be 90 minus phi. So this mg will have a component here, so mg cos 90 minus phi, and along directly perpendicular we will have mg sin 90 minus phi. So this is mg sin phi and this is mg cos phi. Okay, so let's copy this whole figure to the next page. Copy here, paste, repaste, and let's just make it smaller. Okay, now along x direction, so we have to find out the velocity. We have to find out the velocity after 2 seconds. So how do you do that? So along x direction we can have vx t equals vx0 plus ax t. So ax is the acceleration along x direction. Okay, so 2 seconds is vx at 0. So in along x direction, what is the initial velocity, which is v sin theta, right? But it is the negative sign, so minus v sin theta plus acceleration along x direction is force along x direction by mass. So force along x direction is this mg sin theta, mass if you divide it by mass, so g sin theta times t. So fine. So Vx at t equal to 2 second becomes minus V is 3 meter per second, so 3 sine theta 15 degree plus 9.81 sine 15 degree times 2, no sorry, sine 5, so sine 10 degree times 2. So if you calculate it, so 9.81 times sine 10 degree times 2 minus 3 times sine 15 degree. So this becomes 2.63, around 2.63 meter per second. Now the same thing we can do along y direction also. So along y direction we have Vy t equals Vy0 plus Ay t. V equals u plus at, that formula we are using. So now Ay, what is Ay? So see, there is no force acting along y direction. So Ay is 0, so Vy at t equals Vy at 0, which is equals Vy at 0 is this V cos theta. So V cos theta, which is 3 times cos 15 degree, I guess. Theta is 15 degree, so 3 times cos 15 degree gives you 2.89 meter per second. So the amplitude or the magnitude of velocity root over Vx at 2 square plus Vy at 2 square. So 2.63 plus 2.89 square meter per second. So what does it give you? Square root of 2.63 square plus 2.89 square, 3.9 meter per second. Easy question. So 3.91 meter per second, this is the right answer. Okay. Okay, so next question. The third and fourth stages of a rocket are moving in deep space with velocity 15,000 kilometer per hour. So this whole thing is moving in space with 15,000 kilometer per hour. When a small explosive charge between the stages separate them. Mass of the third stage is 400 kg. So mass of the third stage is 400 kg, and that of the fourth stage is 200 kg. So this is the fourth stage and this is the third stage. Okay. At separation, the speed of the fourth stage has increased. So speed of the fourth stage has increased to 15,100 kilometer per hour. Immediately after separation, what is the speed of the third stage immediately after separation? So V3 is asked. So simple momentum balance, let's say. So earlier V was 15,000 kilometer per hour. Okay, so now, so the old so old momentum, so momentum balance we will be doing. So m3v plus m4v equals m3 and let's say v3 new plus m4 v4 new. This is new velocity. So v3 new is asked. So m3 plus m4 v by, so minus m4 v new by m3. This is the velocity. Okay, so m3 plus m4 is 400 plus 200, so 600 times v 15,000 minus m4 is 200 times, this is v4 new, right, 15,100 by m3 is 400 meter per second. So okay, so 600 times 15,000 minus 200 times 15,100 whole thing divided by 400. One bracket I need. 14,950. 14,950. Sorry, kmph. kmph. 14,950 kilometer per hour. Okay. Okay, so question number 8, which is the last question for today. So consider the example of rocket motion in deep space discussed in the lecture. Assume that it is impossible to build a structurally sound container that can hold fuel more than one whole fuel of more than 9 times its mass. Let rocket ejects exhaust at speed u. Suppose the rocket starts from 0 initial speed with a full tank of fuel. The final speed of the rocket will be. So let's say rocket is of mass m and velocity v. Okay, and it removes for per unit time. It removes fuel of mass dm at speed u. So this is fuel removed per unit time at with of mass dm at velocity u. And this is the original mass. So at any given unit time, the momentum of the whole system is mv, which should be equals the momentum of okay, so the momentum of the rocket plus the momentum of the fuel that was that is ejected. So let's say whenever the fuel is ejected, the velocity of the rocket will increase a little bit. So let's say the increase in velocity of the rocket due to the ejection of the fuel is dv. So dv amount of it is getting increased. So mv, it was the earlier, and which becomes, so m minus dm, it has rejected, and the velocity becomes v plus dv. Okay, plus only the fuel has mass dm and the velocity is v minus u. So v was its original velocity direction and it was getting removed like this, so at u at the opposite direction, so v minus u. So let's solve this. So mv equals mv plus m dv minus v dm minus dm dv plus v dm minus u dm. Okay, so mv cancels, v dm cancels, and dm dv we ignore. So 0 equals m dv minus u dm. Okay, now so as dm amount of fluid is burning, so as the fuel burns, the mass of the rocket is also decreasing, right? So we can write the change in mass of the rocket is negative of this dm. So whatever fuel has burned, that much amount of mass the rocket has lost. So we can write dm, like you can write dm is equals minus d capital M. So we get ud small m equals mdv. So minus ud capital M equals mdv. Fine. So dv becomes minus u dm by m. Now if we integrate this from some m initial to m final and from 0 to v, so v becomes minus u log m mi to mf. So v equals, we observe this negative sign, so u equals log mi by mf. So v is this. Okay, now the question is container can hold fuel more than 9 times its mass. So initial is final plus 9 times its final. So container can hold it's more than 9 times, so 10 mf. So v becomes u log 10 mf by mf. So u log 10. So the correct answer is this. Okay, simple.